Welcome, architects. When we discuss AI scaling, we often focus on parameters and token counts, but the real bottleneck isn't the code, it's the physical orchestration of electrons across silicon. We are moving away from the era of discrete servers and into the era of the superpod. Think of a single H100 cluster not as a collection of nodes, but as a singular distributed machine. In this session, we will peel back the abstraction layers of the GPU interconnects and memory hierarchies that make LLM training possible. If you design for high availability, you need to understand why a single bit flip on one of 10,000 GPUs can stall a multi-million-dollar training run. This is the machine that makes AI possible.
To understand the scale, we must look at the individual unit of compute. An H100 Tensor Core GPU isn't just a processor, it's a massive parallel throughput engine. With 80 billion transistors and the capability of delivering up to 4 petaflops of FP8 performance with the transformer engine, the sheer density of compute creates immediate infrastructure challenges. This isn't your standard x86 architecture. We are dealing with massive register files and shared memory spaces that must be fed data at a rate traditional PCIe buses simply cannot handle. We are looking at a TDP of 700 watt per unit, which changes how we think about power delivery and thermal headroom at the rack level.
The biggest lie in computing is that flops matter most. For AI, it's all about memory bandwidth. Standard DDR5 RAM is a snail compared to HBM3E. We are talking about 141 gigabytes of HBM3E memory, providing 4.8 terabytes per second of bandwidth. Why does this matter? Because in LLM inference and training, the weights must be moved from memory to the compute cores constantly. If your bandwidth is too low, your 4 petaflop processor is sitting idle 90% of the time. This is the memory wall. HBM3E uses vertical stacking, TSVs, or through-silicon vias, to achieve this throughput, placing the memory physically on the same package as the GPU logic.
When you have 8 GPUs in a single HGX baseboard, they need to talk to each other as if they were one chip. This is where NVLink comes in. Unlike PCIe Gen 5, which caps out at 64 gigabytes per second, NVLink 4th and 5th Gen provide up to 900 gigabytes per second to 1.8 terabytes per second of bidirectional bandwidth. This creates a unified memory space. As an architect, you must view NVLink as a non-blocking switch fabric. It allows for GPU direct P2P communication, bypassing the CPU entirely. This is crucial for all reduce operations, where every GPU needs to sync its gradients with every other GPU in the node, without hitting the bottleneck of the system bus.
How do you fit a 1.75 trillion parameter model into 14.1 gigabyte of VRAM? You don't. You shard it. As infrastructure engineers, you deal with 3 main types of parallelism. Data parallelism splits the batch across GPUs. Model parallelism, specifically tensor parallelism, splits individual layers across GPUs within a node using NVLink. And pipeline parallelism chunks the model layers across different nodes. Each requires a different networking profile. Tensor parallelism is extremely sensitive to latency, requiring the sub-microsecond speeds of NVLink, while pipeline parallelism can tolerate the slightly higher latency of the scale-out network. Mapping these to your hardware topology is the difference between linear scaling and a total collapse in efficiency. Once you go beyond 8 GPUs, you leave the world of NVLink and enter the world of the scale-out network. For AI, standard Ethernet is often insufficient due to its lossy nature and high overhead. We use InfiniBand, or ROC, RDMA over Converged Ethernet. These technologies support Remote Direct Memory Access, RDMA, allowing one GPU to write directly into the memory of a GPU in another rack without involving either operating system. We are looking at 400 gigabits per second to 800 gigabits per second per link with sub-microsecond latencies. In a cluster of 32,000 GPUs, the network topology, usually a fat tree or dragonfly, becomes the backplane of your data center computer. The laws of physics are the ultimate limiters of AI. A single rack of H100s can easily pull 40 kilowatt to 100 kilowatt of power. Traditional air cooling is reaching its breaking point.
We are seeing a massive shift toward liquid-to-chip cooling and rear-door heat exchangers. For the senior architect, this means site selection and infrastructure design must account for liquid loops and high-density power distribution units. If your cooling fails for even 10 seconds, the thermal throttling on these 700-watt chips will cause a massive drop in T-flops, leading to a synchronous hiccup across the entire distributed training job. Precision in power delivery is no longer optional. In a cluster of 20,000 GPUs, the mean time between failure, MTBF, of a single component is high, but the probability of at least one failure during a 30-day training run is nearly 100%. Because training is synchronous, using NCCL collectives, if one node fails, the entire cluster stops. We solve this with frequent checkpointing to high-performance parallel file systems, like Lustre or Weka. However, checkpointing a multi-terabyte model state every hour creates a massive I/O burst. Architects must balance checkpoint frequency against I/O overhead and implement in-network computing to detect and isolate faulty nodes within milliseconds to restart from the last known good state.
Hardware is nothing without the software that orchestrates it. CUDA is the bedrock, providing the low-level primitives for memory management and kernel execution. But we are seeing a shift toward higher-level abstractions, like OpenAI's Triton, which allows developers to write highly efficient GPU code without mastering C++ or PTX assembly. The goal is memory coalescing, ensuring that multiple threads access contiguous memory locations to maximize that 4.8 terabytes per second HBM bandwidth. As an architect, you need to ensure your software stack, from the driver to the container orchestration in Kubernetes, is tuned for GPU direct storage and topology-aware scheduling to keep the pipes full. We are currently looking at the transition to the Blackwell architecture. Blackwell pushes the limits further with 20 petaflops of FP4 compute and a 20x performance increase for LLM inference. It introduces a dedicated decompression engine and second-generation transformer engine. But the real story is the NVLink switch chip, which allows up to 576 GPUs to talk to each other in a single NVLink domain. We are moving toward the 100,000 GPU cluster. For you, the senior software architect, the challenge is no longer about managing a server. It's about managing a planetary-scale compute fabric. Master these interconnects, and you master the future of AI.